So let's start with module 3. This module deals with protection issues for microgrid, smart grid, introduction to smart meters, and intelligent electronic device. So let's protection of a typical microgrid. Figure shows the protection of a typical microgrid. Here we can see different sets of circuit breakers and centralizing circuit breaker to isolate the different sessions. And here we can see MCBs. They are connected to the different DG units and different customers and to different storage units. And here the CBs are used to isolate microgrid from the main grid. And so to guarantee the stable operation of a microgrid during contingencies, two major issues that must be dealt. They are, we need to find out the instance at which the microgrid have to be islanded under a particular contingencies, and to isolate the microgrid and give sections with different coordinate fault protection. And when we switch on from change off from grid control to islanded or standalone mode, there will be a clear reduction in microgrid fault level. Okay, so operation and sensitivity of some relays may be get affected, and rapid islanding during non-fault situation can be mainly achieved if we do install high-speed communication channels between these two grids, that's utility and microgrid. And coming to islanding, as you know, microgrids, they do have normally a capacity less than 10 MVA, and that is very small when we compare with utility, and it should have enough generation to supply major parts of its loads. And if suppose if islanding does not occur at PCC, then the microgrid may carry a part of the utility with it. So and some limitations are there in terms of technical and cost of implementation, and these two factors are also has to be considered while designing the microgrid protection schemes. So the issues need to be considered for islanding are, the first one, whether the speed of operation of protection system need to approach SEMI F47 specifications. SEMI F47 specification is nothing but it's a specification for semiconductor processing equipment voltage sag immunity. Like it specifies the required voltage sag tolerance for a semiconductor fabrication equipment. And the second issue need to be considered is how to minimize the speed of separation, whether non-fault separations will be allowed, like under voltage, open phase voltage, and balance conditions, etc. And separation protection limitations imposed by exporting microgrid. Exporting microgrid means microgrids which engage in power trade, and whether the resynchronization to utility would be automatic or manual. So these are some issues need to be considered for islanding. So let's see different islanding scenarios. The first one is fast separation from the faulted feeder. Second one, the prevention of speedy separation, especially the nuisance separations. And third one, non-fault separation. And the fourth, separation from exporting microgrids. And last one, resynchronization. So first, let's move to first scenario, fast separation from the faulted feeder. So coming to the first one, fast separation from the faulted feeder. Existing protective equipment is not fast enough to clear the fault in less than 50 milliseconds. Fast separation is very essential for voltage sensitive loads like electronic equipments, etc. And a medium voltage breaker, it requires 3 to 5 cycles to interrupt the circuit after receiving the trip signals. Usually one cycle lasts for 20 milliseconds. So in and around, so if this MV breaker, it requires approximately 100 milliseconds to interrupt the circuit after receiving the trip signal. And this may also damage the voltage sensitive loads. So this microgrid should be very fast, and they do act very fast. Okay, and so other means to prevent the voltage from falling below 50% or for 3 cycles or longer. So the cases to be considered to design and to improve protections are when separation is not necessary and when separation is mandatory. So let's discuss the first case. So here we can see two feeders, feeder 1 and feeder 2. And suppose when fault occur at feeder 1, what happened? it reduces the bus voltage, right? So which means this feeder 2 can also may get tripped. So if fault occur in one feeder, it reduces the voltage in another feeder, and that is picked up by this relay and tripping the feeder. So this is the case where when the separation is not necessary, means if the fault is not located in between the coupling point and the utility substation breaker. We can see different types of faults are the phase to ground, phase to phase to ground, three phase to ground, etc. Okay, so all these type of faults have different effects on power system and the relays of protection equipments, and should be react as soon as possible once the fault occurs. Another option is to prevent sag is to install electronic sag corrector, which is very expensive. Or we can replace the star content transformer with delta star content transformer, and that is very cheaper. And we can also add a high voltage side breaker. And usually for single phase to ground faults in the utility, delta star transformer would ensure that the phase to ground voltage in the micro does not drop below 58%. So let's see this how it is. So here we can see when there is no open delta, that is in the normal case. So in the normal case, we know the voltage VL is equal to V phase and IL is equal to 1.732 I phase, and this VA rating, it is given by 1.732 VLIL. That is, finally we can get the value 3 V phase I phase. In case of this is a normal case, but coming to open delta case, here unlike this normal case, this IL is equal to I phase and VL is equal to V phase, and the VA rating is 1.732 VLIL, which gives 1.732 V phase, which is equal to root 3 V phase I phase. So for normal, the VA rating is 3 V phase I phase, and for open delta, it's root 3 or 1.732 V phase I phase. So VA rating for open delta, VA rating of closed delta is 1.732 V phase I phase by 3 V phase I phase, which approximately equal to 58%. So there is a open delta or delta connection. It will ensure we need to ensure that output voltage will not fall below 58%. And we can also make use of the sag protector to hold the voltage up to 3 cycles, and a combination of electronic sag correctors and high speed relaying, they can satisfy the F07 requirements for rapid fault clearance. And kick block fuses along with sag correctors can also be used within the microgrid. And if utility amplifiers or current tripping of the feeder for fuse saving purposes, then separation of the microgrid will be required. So all the protected device, it should be fast enough to meet the specified fault clearing time. That's the main thing. Okay, so if we can replace that star transformer with delta star, one is a cheaper solution, but it is less effective, and we can make use of SME F07, which allows the sags below 70%. And the only thing, as I said before, we need to keep all the protected devices or everything, that all should be fast enough to meet the specified fault clearing time. And this delta star connection is effective only for single phase to ground fault on the delta side and for load sensitivity line and neutral on the star side. So let's come to the case when separation is mandatory. So when fault occur on its main incoming feeder at the PCC, or you can say the fault point fits at the upstream to the PCC breaker, we need to immediately separate this microgrid from the utility grid. So separate is also mandatory for high-speed separation utility protection requirements without maintaining even along the voltage title utility. And when we need to develop high-speed protective devices that meets SEMI F07 standards. Coming to the second scenario, scenario, it's prevention of spurious separation, or it's also called nuisance separation. So the major cause of fault strip and this spurious separation is the poor quality of devices, and the technical standards, they do specify the voltage and frequency trip settings for measurements made at the PCC, but the problem is that this does not find the exact fault location. So the only reliable method of fast tripping the PCC breaker is to have a transfer trip from the utility grade substation breaker. And both the relays, electromechanical relays and microprocessor based protection system, they do face fault stripping problems as they fail to locate the exact fault location. And for a single microsource, a fault strip amounts to losing kilowatt hour sales for a brief period, and the cost incurred to restart and resynchronization. For a microgrid, a fault strip, it leads to significant power quality problems, and if microgrid has enough storage, then this this spurious separation can be tolerated. If unacceptable voltage deviation persists longer than the allowable limits, then the separation is mandatory. So the effects of spurious separations are the unwarranted outages to non-priority loads, and for exporting microgrids, it will lead to loss of revenue and trust. So coming to the third LND scenario, non-fault separation. So in some situation, it is necessary to disconnect microgrid from utility grid even if there is no fault. And this will typically happen due to low voltages or under voltages. And the microgrid and the utility may also negotiate a trip control to coordinate with the voltage limits for balanced voltage condition as specified by SEMI F07 and IEEE standards. And only when we have to separate microgrid, we can't say that all feeders have a load balance. A degree of unbalance will be there. Then the under-voltage tolerance limit for the microgrid mainly depends on factors like transformer connections and grounding points within the microgrid, and some loads, it will be highly voltage sensitive. So the sensitivity to voltage and balance of loads, microsources and other equipment, it should be considered to determine the criteria for establishing this under voltage tolerance limit. And a voltage unbalance may be caused internally or externally to a microgrid. For that, an intelligent controller function should be incorporated, PCM at the PCC, to make the decision of separation. That is, we need to incorporate an intelligent controller to make proper decision of separating microgrid from utility. So the third issue is open phases, somewhat common problem in power system. Sometimes we know some of the fuses will blow out, making one of the particular phase open. So any phase, fuse between the utility and PCC, if it's blown out, it will lead to open phase condition. So it's better if we avoid fuses between utility and PCC. And the second point is detection of non-fault open phase is difficult. As we know, if open phase occur due to fault, it's easy to detect. But if it's due to non-fault condition, it is difficult to detect that. Then open phase conditions are potential hazards to transformers and microsources, because it leads to overcurrents and voltage, and it may damage the microsources, transformers, etc. And it also causes problems to persons who are working on the line. And as I said before, it's better if you do avoid fuses between PCC and utility substation. Coming to the fourth one, separation. So let's see the fourth scenario, separation of exporting microgrid. So microgrid, it can be a exporting microgrid, or it can be an inverting microgrid. So inverting microgrid means we are not giving any power to the grid, just we do take the power from the grid, that's it. But exporting microgrid means the power we can take and we can give the power to utility. Okay, so that's exporting microgrid. And as we know, the generation is usually it will exceed microgrid load requirement in case of exporting microgrid. So the main problem is that the utility contingency may lead to unintentional power flow from the microgrid to the utility. That is a problem. If a problem in utility is that utility contingency, it might lead to an unintentional power flow. So if microgrid is importing microgrid, we can employ a reverse power relay, and this relay should be connected to circuit breaker to island the microgrid in case of a reverse flow of power. But in exporting microgrid, we can't use a reverse relay because here we have contract to supply power. So in exporting microgrid, there will be an excess of power. So its impedance ratio is closer to that of utility. That's a major difference between an exporting microgrid and an importing microgrid. And a redesign of the protection control system is under research now. So coming to the last scenario, resynchronization. So resynchronizing are carried usually using relay and control schemes, and if the microgrid has only one source, micro source, then the choice for automatic or manual resynchronization depends mainly on on availability and skills of the operator. And if multiple micro sources are there at various location, and automatic resynchronization schemes, it should be incorporated in PCM design. And a PCM should also have some advanced control schemes like delayed resynchronizing during storm conditions where disturbances may be frequent, and communication facilities with at least the larger micro sources. So with this, we come to the end of the different islanding scenarios.